Namaste everyone, welcome to physics class photoelectric effect. We have seen how did Einstein explain the photoelectric effect observations made by Leonard Hallward and Henry Church using quantum theory, and how satisfactorily his explanations gave solution to all the practical observations, right? Namaste. So Einstein's equation was h nu supplied energy is equal to h nu naught energy required to remove the electron, remaining energy kinetic energy. It is a law of conservation of energy. So in this chapter, let us see what are the important parts that you have to concentrate. All the definitions like you have work function, then threshold frequency, threshold wavelength, stopping potential, photoelectric emission, thermionic emission, and all the definitions. And then some questions. First of all, the experimental apparatus setup made by Leonard and Hallward. What are their observations? And what first the experimental setup, what did they do? And you have that picture in the book itself, right? And if it is asked, not very important question, explain the experimental technique used by Hallward and Leonard, and you have to explain it, right? You have that with a suitable diagram, explain the experimental study of photoelectric effect. And you have this answer in your book and have explained it everything. Just I want to make it clear for which question which answer you have to write. This is a chapter where you usually find that difficulty. Which question, what answer I have to write, whether it is Einstein's explanation or experimental observation, whether I have to explain the experimental study. This is experimental study of photoelectric effect, and there is a battery, there is a vacuum tube, there is a quartz window, and ultraviolet light is put over this, electrons come out, they are collected by anode, and that flows through a ammeter, microammeter, current is read, and there is a potential which can be converted or reversed, current can be reversed using commutator. All those explanations. I didn't put the diagram because I have drawn it many a times. Next question is, write the experimental observations of photoelectric effect. Not Einstein's explanation. Experimental observations of photoelectric effect. That there is a minimum frequency below which the photoelectric emission doesn't take place and all. We will see those experimental observations. And you see how many times it is asked. March 2016, 5 marks. And model question paper, March 2017. So it has been asked many times. 5 observations or 4 observations, 5 marks, right? And we will see one by one. What are the way in which those questions can be asked. One is write the experimental observations of photoelectric effect. Mention any 3 experimental observations of photoelectric effect, 3 marks. Then what are the experimental features and observations of photoelectric effect? First one, for a given photosensitive material, there is a minimum frequency of radiation. Above the threshold frequency, the photoelectric current is directly, above the threshold frequency, if your radiation is capable of removing electrons, then for those photoelectric current is directly proportional to intensity of incident radiation. You know it. When the intensity of incident radiation is more and more, the photoelectric current is more and more. Einstein's explanation is different. He says it is the more number of photons falling when you increase the intensity, more electrons are removed, current increases. That is different part. But they say, Hallward and Leonard say, simply as intensity increases, the photoelectric current increases. But this happens only when the incident frequency is greater than threshold frequency. One thing. Second one, for a given photosensitive surface and frequency of incident radiation, the saturation current is proportional to intensity of incident radiation, whereas stopping potential is independent of intensity. Saturation current is depending on incident frequency of incident radiation. What do you mean by that? Stopping potential versus photoelectric current. The saturation current is proportional to intensity. Suppose you go on changing the intensity, you are not changing the energy of photons, right? So stopping potential is same. And if you are making this for first intensity, if you increase the intensity of light, if you increase the brightness of light, what happens? More photons come, more electrons are liberated, and that produces more current. So you will land up here. But stopping potential is same because you have increased the number of photons, you have not increased the energy of each photon. Similar photons in large number are put when intensity is increased. So that increases the photoelectric current because more electrons, but their energy is same. So what is the energy required to stop them? Same as previous. With how much energy? 50 electrons were stopped. With the same energy, for 100 electrons have to be stopped, because each electron is having the same kinetic energy, because intensity doesn't increase the frequency. We have increased the intensity. So that is what is told here. For a given photosensitive surface and frequency of incident radiation, saturation current, the maximum current, because when all the electrons reach the anode, you can't expect still more electrons reaching the anode. You have got the full current, right? All the electrons emitted from the cathode, when they reach the anode, full current is obtained. So that current is this one. Saturation current depends on intensity. It does not depend on the stopping potential, whereas stopping potential is independent of intensity. And even if you increase the brightness, photoelectric current changes, but not the stopping potential. That is the meaning. Hope you have followed it, right? So when the intensity of incident radiation is increased, the saturation current keeps on changing, but the stopping potential remains the same. Einstein's explanation is, when you increase the intensity, you are giving more and more photons, but they will remove more and more electrons, but of the same kinetic energy. So energy needed to stop is same. Okay, that is the second one. What about the third one? So first one you have followed, right? There is a frequency of incident radiation. The photoelectric current is directly proportional to intensity. Okay, then second one is over. Then third one. For a given photosensitive material, there exists a certain minimum cutoff frequency, and above which only you will get photoelectric emission, below which there is no photoelectric, that is called threshold frequency. So for a given photosensitive material, there exists a certain minimum cutoff frequency of incident radiation called threshold frequency, below which emission of photoelectric emission, no emission of photoelectrons takes place, below which no emission of photoelectrons takes place. No photoelectric emission is possible below threshold frequency. That is simple. Yes. Fourth one, above threshold frequency, stopping potential or maximum kinetic energy of emitted photoelectrons. Because more the kinetic energy, you need more stopping potential. Stopping potential or maximum kinetic energy of photoelectric electrons increases linearly with the frequency of incident radiation. As the frequency is more and more, kinetic energy of electrons is more and more, right? So this is kinetic energy or stopping potential, and this is frequency. And this is threshold frequency. Above threshold frequency, the stopping potential or maximum kinetic energy of emitted photoelectrons increases linearly with frequency of incident radiation, but is independent of intensity. So if you change the brightness, kinetic energy has nothing to do with that, but kinetic energy changes when the frequency of incident radiation increases. The photoelectric emission is an instantaneous process, and the time gap between the photons going and giving energy to electrons and electrons coming out is only 10 to the power minus 9 seconds, nanoseconds, or even less, 10 to the power minus 8 seconds. Okay, so that is the explanation, right? This is experimental observations, experimental features. What did Leonard Hallwork and Henry Church observed in the practicals? They didn't explain. They observed that these things are happening in the experiment, and they did experiment with all these things. Why it is so, explanation is not given. Okay, that was given by Einstein. Yeah, this is another important question. Write Einstein's equation of photoelectric effect. Give Einstein's explanation of photoelectric effect, right? And on experimental observations. What observations Leonard Hallwork gave, on that, how did Einstein give explanations? So that is this one. First, Einstein's equation, photoelectric equation, H nu is equal to H nu naught plus kinetic energy. H nu naught is work function, right? Minimum energy required to remove the electrons. But what is kinetic energy? Okay, kinetic energy maximum. We are interested with that electron which is more energetic. We must get ready to stop that electron itself. Once you are able to remove that most energetic electron, there is no question of worrying about less energetic electrons. So what is the kinetic energy? H nu minus work function is equal to kinetic energy maximum. and that is the equation. Of course, this goes here. You have to just adjust it, but it is here, right? Kinetic energy maximum is the maximum kinetic energy of photoelectrons. H is Planck's constant, and nu is the frequency of incident radiation. Phi naught is the work function of the metal. You have to explain the terms. That is very important. Yes, moving on. What are the Einstein's explanation? In the equation, kinetic energy maximum is equal to h nu minus phi naught. Work function phi naught is a constant. This is a constant. It depends linearly on frequency. Phi naught is a constant. Kinetic maximum is directly, h is also a constant, directly depending on the frequency. That means more the frequency of incident radiation, more is the kinetic energy. More the money your father gives to you, more will be the remaining money with you, right? So because what the money you spend for traveling, phi naught is a constant. So phi naught is a constant, h is a constant, so kinetic energy of the photoelectrons increases with frequency linearly, yes. As the frequency is increased, kinetic energy of photoelectrons increases. There is no term representing the intensity of light in the above equation. Do you get the intensity anywhere? No. So in the kinetic energy equation, there is no intensity. So kinetic energy of photoelectrons, that what the money that you remain with, it doesn't depend on the intensity of incident radiation. So kinetic energy of photoelectrons is independent of intensity. Okay. Second one. Since kinetic energy maximum cannot be negative from equation h nu minus phi naught, right? So you can replace this as h nu naught. H nu minus h nu naught is equal to kinetic energy maximum. We will use it like this. H nu minus h nu naught is equal to kinetic energy maximum. And again, h nu is greater than h nu naught. That is, supplied energy is greater than the required energy. That means you are given with more money than what is required for traveling. You will travel then. Kinetic energy is positive. If h nu is greater than h naught, nu is greater than nu naught, then nu naught is the threshold frequency. Hence threshold frequency is the minimum frequency. So they conclude it like this: kinetic energy should be always positive. If it has to be positive, this should be greater than this one. So the threshold frequency is the minimum frequency for radiation to of radiation to remove the electrons. So that is the explanation. It implies that here they say that h nu h nu is greater than phi naught. Otherwise kinetic energy will be negative. So h nu is greater than phi naught. Kinetic energy maximum is h nu minus h nu naught. That means work function, if it is equal to h nu naught, what to do? I don't see that, right? Now, since I can show it here. Since kinetic energy maximum cannot be negative from the equation, if this cannot be negative, h nu minus phi naught, h nu should be greater than phi naught, or kinetic energy maximum equal to h nu minus h nu naught, where phi naught is equal to h nu naught. Yes, this is replaced by h nu naught. If therefore h nu should be greater than h nu naught, that should be nu should be greater than nu naught, where nu naught is the threshold frequency. Hence, if kinetic energy should be always positive, that means if the electrons have to come out, then h nu should be greater than h nu naught, or nu should be greater than nu naught. Then only this is positive. Otherwise electrons have not come out, they are inside the material, and they are bound, they are not free. So then kinetic energy becomes negative. It is meaningless actually. Hence threshold frequency is the minimum frequency for a metal surface, right? And what else? Third one, intensity of radiation is the number of photons. That explanation I was giving from the beginning. Intensity of radiation is the number of photons per unit area, per unit time, for nu greater than nu naught. If the frequency is sufficiently larger, as intensity of radiation increases, number of photoelectrons increases, number of photons increases, and the number of photoelectrons emitted increases, because each photon removes one electron, and this increases photoelectric current. Yes. According to Einstein, the basic process involved in the photoelectric effect is absorption of light by quantum by an electron. Electron absorbs one photon, which results in an instantaneous transfer of energy, hence the process is instantaneous. So according to Einstein, it should be a particle-particle collision. As photon goes, electron absorbs energy, comes out. The time needed is very less. It is not a wave process, it is a particle process. Okay, it's an instantaneous process. Yeah, we will move on to some, and all the graphs, I have not included the graphs. That there is no confusion in that. Explain, okay, I will just deal with that once. Explain intensity versus photoelectric current. They are dependent. Graph. Intensity versus photoelectric current. Current versus intensity. More the brightness, more will be the photoelectric current. Kinetic energy versus threshold frequency, or stopping potential versus frequency, like this, right? This is threshold frequency, this is frequency here, this is threshold, and here is the stopping potential, right? And this is negative stopping potential, that means this is work function. Then photoelectric current versus stopping potential for different intensity. Different intensity means different current, but stopping potential same, right? So more brighter, less brighter, very less brighter, because photoelectric current is lesser and lesser, but same stopping potential. Last graph. Different frequency, photoelectric current versus stopping potential. Photoelectric current versus stopping potential for different frequency. That means you are increasing more and more frequency, more and more energetic photons, you know it. When more and more frequency light is incident, more and more energetic photons will be falling, and they will be liberating more and more kinetic energy electrons. Stopping potential will be more and more. So this is for lesser, but number of photons are same, so photoelectric current doesn't change. This is stopping potential 1, stopping potential 2, and stopping potential 3. More stopping potential means this is for more frequency, less frequency, less frequency. Nu 1 should be greater than Nu 2 should be greater than Nu 3. All these graphs are very important. Try to understand them. If you have still doubts, please write and ask me. That is very important part, right? Now we will go to the problems. Yes, first one. Find the frequency of light, which, this is in your PDF, right? You need not write it, just read it and try to solve it. So have a pen and paper first of all, and then a calculator, then be ready with all those things. Don't look at me when I solve the problems. You must do that yourself. So here, find the frequency of light which ejects photoelectrons from a metal surface, which are fully retarded by a potential of 4 volts. So stopping potential is 4 volt. Stopping potential 4 volt can stop all the photoelectrons. The threshold frequency of the metal, nu naught, is 5 into 10 to the power 14 hertz. That is the threshold frequency. Okay, we have to find the frequency of light which ejects photoelectrons. What is the incident frequency? Nu. Nu naught is the minimum frequency required. So find the incident frequency. If threshold frequency is this, that one, and stopping potential is this one. And from the stopping potential, you can find out kinetic energy. You know this, right? How to find out the kinetic energy? You know that potential difference between any 2 points is the work done in taking the charge. Potential difference of a battery is the work done by the battery in sending the charges. W by Q. What is W? QV. So what is the kinetic energy of photoelectrons? Kinetic energy is equal to EV naught, that is 1.6 into 10 to the power minus 19 into 4 volt. I can write it, so much of joules, right? You keep on writing it. So once the stopping potential is given, that itself is not kinetic energy, but it can be used to find out kinetic energy. Just multiply by the charge of electron. Okay, so stopping potential is 4 volt. That means 4 volt into charge of electron gives the energy of electrons. Okay, write the Einstein's formula. Incident energy h nu, work function h nu naught, energy to remove, plus kinetic energy maximum. Maximum kinetic energy of photoelectrons, of course, that is itself, because 4 volt can stop the fastest electron, means that itself is the highest kinetic energy. Okay, now, and h is Planck's constant. You must know all these things. 6.6 into 10 to the power minus 34 joule second. That is Planck's constant's value. Planck's constant, charge of electron, mass of electron, speed of light, all these things are very much needed. Just try to remember them once or twice, enough. Then when you use it every now and then, you will permanently remember it, no problem at all. Need not by heart it. Just try to remember it once or twice. So 6.6 into 10 to the power minus 34 joules per second, joule second, H. Now, shall we substitute? They are asking nu. Nu naught is given. Kinetic energy maximum we have in our hand. So just substitution. H. 6.6 into 10 to the power minus 34. What is nu naught? 5 into 10 to the power 14 hertz is equal to H, again 6.6 into 10 to the power minus 34 joule second into nu naught, nu you have to find out. Wrong substitution. 6.6 into 10 to the power minus 34 into nu. Frequency of incident radiation is to be found out. Is equal to 6.6 into 10 to the power minus 34. Nu naught is 5 into 10 to the power 14. Remember, our answer nu should be greater than this. Do you know why it is so? Because any frequency removes electrons means it should be greater than threshold frequency. So nu should be greater than 5 into 10 to the power 14. Plus kinetic energy maximum already got 1.6 into 10 to the power minus 19 into 4 joules, right? So EV naught, kinetic energy, is always charge into potential difference, because work done in taking the charge by the battery is the potential difference. Okay, 6.6 into 10 to the power minus 34 into nu is equal to, I think I can multiply this, 5 into 6, 30, 5 into 6, 30, 33. 10 to the power minus 20, correct? Minus 34 plus 14, 20 plus 6.4, 24, 6.4 into 10 to the power minus 19. And if I want to add these two, both should be the same 10 to the power. So shall I change it here only? This is 33. I want to make this 10 to the power minus 19 as it is here. What I can do? 1 10 to the power minus 1, I can donate it to 33. What it becomes? So shall I do it here only? 3.3 instead of 33, 10 to the power minus 19. Is it okay? 33 into 10 to the power minus 20, 1 10 to the power minus 1 to this, 3.3 into 10 to the power minus 19. So when I add it, 6.6 into 10 to the power minus 34 into nu frequency, this is 9.7 into 10 to the power minus 19. 6.4 plus 3.3. What is nu? Nu is equal to 9.7 into 10 to the power minus 19. 6.6 into 10 to the power minus 34. That is equal to hertz frequency. So shall we calculate it? Yes, I have calculator. You too do it yourself. 9.7 divided by 6.6, that comes to 1.469 into 10 to the power, this is plus 34 minus 19, 15, right? 10 to the power 15 hertz. But what is incident frequency? It is 5 into 10 to the power 14. 14 means I can give 110 here. 10 to the power 15 this one. 110 here means 14.69. 10 to the power 14. 110 you donate it to this one. Then it becomes 14. 10 to the power 14 then. 14.69 into 10 to the power 14 hertz, which is greater than 5. So we got the correct answer. So remember, you have to remember all the formulas, right? The different ways in which you can write Einstein's photoelectric equation. How? See, H nu is equal to H nu naught plus kinetic energy maximum. H nu is equal to H nu naught plus EV naught. Kinetic energy maximum is equal to charge of the electron into stopping potential. Hc by lambda in terms of wavelength. Hc by lambda naught. Of course, here you can simply write work function phi naught, Hc by lambda naught plus kinetic energy maximum. So in this way also you can write it. There are numerous ways in which you can write it, right? So, and one more, h nu is equal to h nu naught plus half mv maximum square. Kinetic energy is half mv square. V maximum is the highest velocity electron. Okay, so we have finished this. Hope you have followed. If you have not followed, please ask me, don't hesitate. That sir is busy and sir, we don't have any time to answer. You just ask me, I will answer in my own time, no problem. Shall we move on to the next question? Yes. Find the frequency of light is over. Ultraviolet light of frequency 2 into 10 to the power 15 Hertz. Okay, nu, not threshold frequency. Ultraviolet light of frequency 2 into 10 to the power 15 Hertz is incident on a metal of threshold frequency 10 to the power 15 Hertz. Threshold frequency 1 into 10 to the power 15 Hertz. Calculate the velocity of photoelectrons emitted. V is how much? Okay, let it be. Yeah, h we know, right? You have to use this equation. Why? You know h, nu is given, nu naught is given, m mass of electron you must know. You must know this, mass of electron is 9.1 into 10 to the power minus 13 kg, must be known. Charge of electron must be known. Now let us use this formula. H nu, because you can understand, nu naught, V and everything should be included in the formula. Work function plus kinetic energy maximum. And out of that, this is the thing which you have to find out. Maximum velocity of photoelectrons. Okay. H nu 6.6 into 10 to the power minus 34, incident frequency 2 into 10 to the power 15 Hertz equal to H 6.6 into 10 to the power minus 34, nu naught 1 into 10 to the power 15 Hertz plus half 9.1 into 10 to the power minus 31 kg. V maximum square. Hope you are also doing with the calculator and all. You must do that. Otherwise of no use. You must do it. Okay. We will finish this and bring this here. 6.6 and 2 and everything is common, right? One thing I can do. This is here. Everything 6.6 into and our all 2 minus 1. It is 1, right? So if I bring it here. Here 2, here 1. 2 minus 1, 1. So what is remaining? 6.6 into 1 into 10 to the power 59. Did you get that? 6.6 into 10 to the power minus 34 and 10 to the power 15. 6.6 into 10 to the power minus 34 and 10 to the power 15. Common. Bring this one here. Inside the bracket 2 minus 1. That's all. 6.6 into 1 into 10 to the power 15. Is equal to, that's all in this, hope you have followed, is equal to 9.1 by 2 into 10 to the power minus 31 V maximum square. Okay, twice this number, once this number, minus 2 minus 1 is 1, only once. So I can bring 2 here, right? Then what it will be? Oh, okay, here one thing is forgotten, 6.6 into 10 to the power minus 34 15, that is common, minus 19, correct? That not 15, minus 19. 10 to the power minus 34 plus 15, minus 19. 2 minus 1 is 1. Now bring this 2 here. 13.2 into 10 to the power minus 19 divided by, I have brought 2 here, 9.1 into 10 to the power minus 31 is equal to V maximum square. That implies, I'll write it here. What is 13.2 divided by 9.1? 13.2 divided by 9.1. 13.2 divided by 9.1 is equal to 1.45. 1.45 into 10 to the power minus 31 plus 31. It is 12. 12. Plus 31 minus 19. 19 plus 12 is 31. So plus 12 is V maximum square. What is V maximum? Square root of this, 10 to the power 6. Of course, you have to write meters per second. Square root of this is 10 to the power 6 meters per second, and square root of 1.45. Square root 1.20. 1.20 into 10 to the power 6 meters per second is the answer. Okay? In calculation, it takes a long process, but the rest of the things are very easy. Right? 1.20 into 10 to the power 6 meters per second, that is the maximum velocity of the electrons. Yeah. 1.20 into 10 to the power 6. Yeah. Shall we move on to the next one? Yes. A beam of light of wavelength 6.8 into 10 to the power minus 7 meter delivers 1 microwatt of power to a photosensitive surface. Okay, 1 microwatt of power to a photosensitive surface. I'll rub this. Yes. Calculate the photoelectric current assuming 10% efficiency. Very different problem. Has nothing to do with the previous solutions. Very special one. A beam of light of wavelength. Wavelength is given. Lambda is equal to 6.8 into 10 to the power minus 7 meters. A beam of light of wavelength, so much meter, delivers 1 microwatt power to a photosensitive surface. Power is 1 microwatt power to a photosensitive surface. Calculate the photoelectric current. I is how much? Current is rate of flow of charges. Amount of charges flowing per second. I is equal to dq by dt. The amount of charge flowing per second. That means amount of charge means how much? Each electron carries a charge of 1.6 into 10 to the power minus 19 coulombs. What is the total charge? How many electrons have been emitted? N into charge of electron divided by dt. That is current. Current is rate of flow of charges. Amount of charge flowing per second. Who is the charge here? Electron. 1 electron charge this much. What about if 10 electrons move? 10 into 1.6. So how many number of electrons move per second into charge of each electron? That is dq. In what time? dt. Now we will restrict all these dt's to 1 second because here power is given. What is power? Power is energy per second, right? That means 10 to the power minus 6 watt means 10 to the power minus 6 joules per second. So we will take this data, and this data is for 1 second. What do you mean by power of a light, beam of light? That power means it is delivering 10 to the power minus 6 joules of energy per second. In every second, it is delivering an energy of 10 to the power minus 6 joules. What do you mean by delivering an energy of 10 to the power minus 6 joules by a bulb or a light? Light contains so many photons. Every photon will contain so much of energy. All the photons together will put the energy on the surface. That energy is 10 to the power minus 6 joules per second. And that energy 10 to the power minus 6 joules per second is not from one photon. It is by the collection of many photons. What is the energy of one photon? That is what you have to go back now. Right? So we say 100 watt bulb. What do you mean by 100 watt bulb? 100 watt bulb means a bulb which delivers 100 joules of light per second. In 1 second it delivers 100 joules. Energy per second is watt, power. So 100 joules in 1 second means it is 100 watt. Who is delivering that 100 joules of energy per second? Photons. Whether it is one photon? No. It is so many photons together delivering the total energy per second. What is the energy of one photon? That is energy of one photon is equal to h nu. Energy of each photon is h nu or hc by lambda, because lambda is given for us. Shall we calculate what is the energy of one photon? Yes, we will do that first. Energy of one photon is equal to h 6.6 into 10 to the power minus 34. Or shall we write a formula and yeah, that we will do. Then we will substitute, right? Energy of one photon is hc by lambda. What is the energy of the beam? 10 to the power minus 6 joules per second. Energy of one photon is so many joules. Now, whether one photon makes this much of energy? No. Because that beam contains many photons. All of them together make 1 microjoules per second or 1 microwatt. Then how many photons will be included in this energy? Can you calculate? Therefore, in 1 second, 10 to the power minus 6 joules of energy is made by how many photons? Did you understand? One photon has got an energy of hc by lambda, but beam is delivering so much of energy per second. That means in 1 second how many photons should be falling? That means hc by lambda of each photon into n number of photons must make that energy per second, 10 to the power minus 6 joules. And all my story is restricted to 1 second now. I am talking everything per second, because this is per second. If 10 to the power minus 6 joules of energy is delivered by the beam of light, how many photons should be responsible for that? If each photon is having an energy of hc by lambda, find out that n. Those many number of photons will fall on the surface. Each photon removes 1 electron. Then how many electrons are removed from the surface? Same n, because every photon removes 1 electron. Same n number of electrons are emitted. How? In what time? In 1 second. Because n photons fall in 1 second and n electrons are removed. If n electrons are removed in 1 second, why can't you calculate the current? Because current is the number of electrons into charge of each electron, total charge divided by time. So you see, one by one how it is connected, right? Beam power is given. That means how many joules of energy it is delivering. And that total joules of energy is delivered by all the photons. How many? N. So each photon, hc by lambda. N hc by lambda should be equal to 10 to the power minus 6 joules. Let us find out how many photons are falling. That implies N is equal to lambda into 10 to the power minus 6 by hc. Correct? Yeah, lambda into 10 to the power minus 6 by hc. What is lambda? Lambda, yeah, 6.8 into 10 to the power minus 7 into 10 to the power minus 6 divided by 6.8 into 10 to the power minus 7 divided into 10 to the power minus 6 divided by 6.6 into 10 to the power minus 34, Planck's constant. C, velocity of light in vacuum, 3 into 10 to the power 8. See how many constants you have to remember. Planck's constant, velocity of light, okay, charge of electron, 1.6 into 10 to the power minus 19 coulombs. Okay, what is this answer? So number of electrons. It should be huge in number, remember. Check it. How much? 6.8 divided by 6.6 is equal to, divided by 3 is equal to 6.8 divided by 6.6, answer. Then divided by 3, answer. 0.343 into 10 to the power. You can't get fraction because 10 to the power should be positive. Is it positive? Yeah, minus 34. This is 10 to the power minus 26. Isn't it? Minus 26 plus 8. Minus 34 plus 8, minus 26. What about this one? 10 to the power minus 13. When I bring it here, plus 26 minus 13, 10 to the power 13. It is a whole number now. Even though this is a fraction, we have 10 to the power plus. So many number of photons. 3, 4, 3 and then 10 zeros. You 3 zeros for this one. 3, 4, 3 and 10 zeros. 3, 4, 3, 0, 0, 0, 0, 0, 0, 0. So many photons will be falling on the surface. So how many electrons are liberated? Shall I write it here? Number of electrons liberated. Liberated in 1 second. Assuming that it is 10% efficient, right? Somewhat I have seen, yeah. Photoelectric current assuming 10% efficiency. Okay. That means only 10% of these electrons, photons will be able to remove the electrons. That one you have to remember. That I have said, I assume that it is 100%. Each photon goes, removes 1 electron. Because some of the photons may not be able to remove the electrons because they might have gone somewhere else. right? And that surface may not have received those photons. That may be the reason. So 10% of these number of electrons, 10% of, otherwise I would have taken the same number, 10% of how much number? 0.343 into 10 to the power 13. What is 10% of so much? 10 times, that is equal to 0.343 into 10 to the power 12 electrons. Correct? That one you have to take it. Only 10% of all the electrons are be able to remove the, and you could have done 10% here itself. That is also okay, right? 10% of this energy is used to remove the electrons. From there only you could have reduced the number. Anywhere you can make 10%. You need not do it here only. You can do the energy 10% and find out the number of photons. Proportionately you will get the same number. So 10% of the total photons are responsible for removing electrons. So the electrons removed is this one in 1 second. Okay, what is current? Current is equal to rate of flow of charges, amount of charge flowing per second, and this is 1 second. I is equal to number of electrons 0.343 into 10 to the power 12 into charge of each electron. This is 1.6 into 10 to the power minus 19 coulombs. That is equal to, so that is current, rate of flow of charges. 0.343 into 1.6, it is 1.09. Oh, you are not getting the answer. 0.343 into 1.6, 1.098 into 10 to the power minus 19, 12, minus 7 ampere, right? We are not getting 5.472, right? Somewhere you have gone wrong. We have to check it now. 1.098 into 10 to the power minus 7 ampere. So 0.343 into 10 to the power 12 electrons, 0.343 into charge of each electron divided by time, 1 second. So 0.343 into 1.6. Oh no, you are getting the answer. This is this multiplication. My calculator is 0.343 into 1.6 is equal to 0.548 into 10 to the power minus 7 amperes. Yeah, what is the answer there? 5.47 into 10 to the power minus 8. It is correct. If you place this here, 5.48 into 10 to the power minus 8 amperes. So very peculiar problem, different one, but you should have an idea of quantum theory to do this, because that is also included in the syllabus. So first, from the beam energy, how many photons? Because one photon has got that much of energy. Together all the photons is the beam energy. So you will get number of photons. That number of photons is equal to that much number of electrons. But if it is given as only 10%, only 10% of electrons. Then those electrons each with the charge 1.6 into 10 to the power minus 19, when they flow in 1 second, flow of charges per second, that is current. So that is the thing. So we will come up with a few more problems in the next class. Till then, keep working all those problems. And do well, don't waste time. So little by little keep on learning. This is the best time to learn all the things. So thanks for watching my class. We will meet in the next class. Thank you.